All right. So last time we just start talking about MIP, which is mercury intrusion porosimetry. So this method just using pressure to push mercury into into the pores of a specimen. Okay, uh, and the pressure can be pretty high. Okay, so the pore size can be measured is around 360 micrometer, and the low pressure up to 2.55 nanometer under high pressure. Okay. The pressure from mercury can be up to 228 megapascal, so that will be corresponding to the smallest pore size. Okay, so we increase the pressure. Okay, so more and more mercury will be penetrated into the pores of the volume, of the pore of the specimen. Okay, and there's a correlation between the applied pressure and the size of the pores. We're going to talk about the equation to correlate these two parameters in a moment. But anyhow, from the pressure to volume of the pores, we can have a correlation between the pore size and the pore volume of the concrete of all other samples. Okay, we can use this method not only for cement and concrete, of course, but also for any type of materials which has pores inside it, okay, including rocks, pigments, papers, okay, and so on. Right? So we could have a correlation between the pore size, the diameter, with the pore volume. Okay, could be cumulative intrusion volume or the total volume or other type of volume such as incremental intrusion volume or differential intrusion volume, okay, or even log. Okay. We can also have a correlation between the pore size and uh, the surface area or the areas of the pores. Okay. All right. Before we talk about the equation correlating between the pressure and the pore size, let's talk about the surface tension and how we can use the mercury to check the pore size distribution of materials. Okay. So let's say we have a single atom in a liquid. Okay. So if that's the case, this atom we have equilibrium force from all the directions. But on the surface, things will change because on the surface, we only have atoms inside the liquid, but not here. Okay, and because of that, we have unbalanced force acting on that atom around the surface of the liquid. So that will cause the curvature of the surface. Okay, so we could have a regenerated balance. Okay, so the surface cannot be a straight line, so it has to be a curvature, so we could have a balanced force. All right, so here talk about the capillary force. So if we insert empty glass, okay, into the liquid, all right, so we're gonna form a curvatures inside the glass and also outside the glass on the surface of the glass. As a result, this is because, again, we need to form a balanced force on atoms near the surface of the liquid. Okay. And the height, the capillary height, h, is depending on the surface tension of the atoms, okay, such as water or liquid. Right. So the work done in moving up the layers, okay, the layers inside the glass tube, okay, due to the surface tension, is covered by this equation. So the work W is a function of surface tension gamma, and the delta A is the cross section of the areas. Okay, so cross section inside the glass, right? So which is a function of the radius of the glass, okay, and also the length. Okay, uh, the work done in pushing the liquid back is covered by this equation. Okay, so volume is the capillary volume, which again is a function of alpha and L. Alpha is uh, the radius, L is the length. Okay. Cosine theta is contact angle of the surface of the liquid. Okay, so the contact angle, or also called red angle of the materials of the liquid. So depending on the type of liquid, the theta or the contact angle will be around this range for mercury. Okay, but let's go back to this equation. So the work done in pushing it back is also a function of surface tension of the liquid, the contact angle, and also delta A. Okay, so that will help us get the Washburn equation. Okay, the Washburn equation will have the final form like this. So the pressure is a function of the surface tension, the contact angle of the materials, and also the size of the pores, the size of the pores. So that's how we can use mercury intrusion porosity to get a correlation between the pore size, alpha, R, and also the pressure. Okay, this is the surface tension of the mercury, and this is contact angle of the mercury, so which does not change too much. Right. So if wet angle is less than 90 degrees, the delta P will be less than 0. Okay, if wet angle is larger than 90 degrees, the delta P will be okay. So sorry, the typo here. So if it's less than 90 degrees, cosine theta will be larger than 0. Okay, so cosine theta will be larger than 0. So the P will be negative. On the other hand, if that angle is larger than 90 degrees, the cosine theta will be negative. So the delta P will be larger than 0. Okay, so cosine theta is less than 0, and here we have negative. So the P will be positive. The P will be positive here. All right. So that means we need a positive force to push the mercury into the pores. Okay. And the higher the pressure, the higher the force we can push into the pores with smaller radius, smaller r. Okay. So for a pore size of 18 angstrom, so this is 18 N, 1 N is equal to 1 time to the power of negative 10th meter. Okay, so 18 angstrom corresponding to 60,000 psi. Okay, based on the Washburn equation. Right, so that's the basic for MIP. To do the experiment, we have 2 steps. Okay, so first of all, we need to prepare the samples. Okay, this is the glass container. Okay, the samples need to be dried out first. Okay, dried, typically overnight. The reason for that is to make sure all the pores is empty. Okay, if there's water in the pores, so mercury cannot get inside the pores. Okay, so we need to dry these pores, but not very high temperature. Maybe so less than 100 degrees Celsius. So temperature cannot be too high, otherwise we may damage the pore structure. Okay, so try to avoid the damage to the pore structure of the samples. Okay, so after the sample is dry, we put that into the glass container here. All right, and the first step is to evacuate the container by vacuum. Okay, so we vacuum the container, and then we slowly increase pressure with mercury. So mercury will be filled here all around the sample and fill the container, the beaker completely. Okay. And then we slowly increase the pressure. The pressure will increase slowly. And we monitor how much mercury is penetrate inside these samples. And based on a washable equation, we can have an idea of the pore size as well as the pore volume. So the pressure will increase slowly. We call that pressurization. And later on, we're going to slowly reduce the pressure. So as you can imagine, more mercury will be extruded outside the pores. We call that depressurization. Right. So the first step is to increase the pressure. And then we reduce the pressure later on. Okay. But we have a difference between increase and reduce, and we call that hysteresis. The reason for the difference between intrusion and extrusion, it is because situations such as the pores has special shape, such as a bottleneck. Okay. The intrusion is caused by increased pressure, and extrusion is caused by decreasing pressure. So in series, if the pores are perfect spherical, okay, so intrusion and extrusion should be the same. Okay. However, at low pressure, the intrusion is in the large interval. Okay, so at low pressure, the volume intruded is in large interparticle voids, which is the voids between the samples. Okay, because the voids between the samples, the size of the pores, is large. But when we increase the sample, the pressure, the mercury will start to penetrate into the pores of the sample itself. Okay, the hysteresis describe the difference between extrusion and intrusion paths. Okay, the volume of extrusion will always larger than the volume of intrusion at a given pressure. Okay, so at a given pressure, the extrusion volume will be high. So this is extrusion. Okay, and this is intrusion curve. So the direction of the pressure will be like this. Intrusion, so we slowly increase the pressure, and then we slowly decrease the pressure. So we call that intrusion and extrusion. And the pressure for intrusion will be larger than pressure at extrusion. For given volume, okay, for given volume. Pressure of intrusion will be larger than pressure of extrusion. Okay, so this is pressure of intrusion, and this is pressure of extrusion. Okay, so pressure of intrusion will be larger than pressure of extrusion for any given volume. Okay. Right. So after this full circle of intrusion and extrusion, the mercury is always retained. Okay, one of the main reasons is because for pores of special shape such as this, okay, the entry for the pores has a bottleneck, so-called bottleneck. It's similar to a container, like this. Okay, so let's assume this is the pores. Okay, the real pore size is this. Okay, but the bottleneck is this much. Let's call that D0 for the real pore size and D1 as the size of the bottleneck. Okay, so the pressure has to be high corresponding to D1, which is smaller than D0. So the mercury can be pushed into this pore. Okay. But when we fill all the pores with mercury and we slowly reduce the pressure, the mercury inside the pores will be trapped because of this bottleneck. So that's why mercury is always retained after reduce the pressure. Okay. But if we keep doing the intrusion, exclusion, the loop may be closed with these cycles. That is because the bottleneck can be damaged, and also the future hysteresis will be smaller. Okay, after these cycles. And each step in intrusion has corresponding step in the extrusion at a lower pressure, okay, as we discussed here. All right, and the first intrusion will fill all the pores without restricted entry. That is another word for bottleneck. Okay, and after the pressure drops, all the pores with restricted entryways with the bottleneck will fill up, and cannot get out of the sample. Okay, so we call that bottlenecking. All right, so after we get the curve of intrusion and exclusion versus the pressure, we can calculate, for example, the pore size and also the surface area. This is a correlation between S, which is the surface areas of the pores, versus the pressure. Okay, theta is contact angle, gamma is the surface tension. Okay, volume V is the volume of the pores. Okay, so we have some assumption to do the calculation. For example, we assume the shape of the pores are cylindrical pores, okay, with a certain radius and certain length of the pores. Okay, so we assume the perfect shape for the pores in order to do the calculation for the surface area, for example. Right, and similarly, we can do the pore size distribution versus the pressure. Okay, for example, these areas is the amount of volume occupied by pores in a certain pore size. Okay. All right, and so pore size distribution can also be get using mercury intrusion pore signature, and also the density, different type of density, such as the bulk density and apparent density or apparent specific gravity. Okay, because this method can also measure the volume, different type of volume of the sample. Okay. But because the pressure applied by the mercury is very high, it's hundreds of thousand psi, so it may damage the real pore structure, which means the measured pore structure may not be the same before the pressure on the mercury is applied. Okay, so this is one of the drawback for MIP method. Anyhow, I will say MIP is a very powerful instrument which can give us a lot of information about pore size distribution, porosity, and also even the surface areas of the sample. Okay. So this is MIP. Okay, so next let's talk about SEM. We have seen the picture of SEM before. It is short name for scanning electron microscopy. Okay, we use electron to scan a sample. Okay, that's why we call it scanning electron. That's two different modes. Okay, one is called backscattered. Okay, which is the picture we see before, like the clinker. For backscattered scanning electron microscope, the sample need to be polished. So the surface need to be a polished surface or thin sections. Okay, we cut the sample. We need to touch the sample with resin. Okay, and then we polish the surface to be very smooth. Okay, similar to what we do to the painting of the car. Okay, we do the primer, we do the paint, and we do polish using different grade of the sand. Okay, so we polish the surface, and then before we do the backscatter SEM. The second mode is called secondary electron detection. It is on fracture surface. Okay, so we can do the no preparation of the surface is necessary as in the backscatter mode. And for both modes, we can use EDS. Okay, we're going to talk about EDS in a moment, but EDS can provide us with information about chemical composition of the materials. Okay. So the secondary electron SEM, okay, they use a special type of electron which collect low velocity secondary electrons, and based on that to produce an image. Okay. And we can see a 3D image, a topography based on secondary electron SEM. Okay, so 3D image is possible, and we do not need to prepare the sample, do not need to polish the sample. Okay. The resolution could be very high, so up to 100,000 times, so much higher than the backscatter mode. Right. So as we can see, this is a sample picture of secondary mode SEM. We can see a topography picture, like a 3D size. Okay. So this is a sand grain. The resolution is 50 micrometer, so not very high here, but it could go to very high resolution. For the backscatter mode, again, we need to prepare the sample or polish the sample. Okay, but it uses a different kind of electron detector. Okay, the speed of electron is higher, high speed backscatter electron. And again, the sample need to be polished and flat. Okay, we need to prepare the sample surface, use epoxy resin, and then we do the polishing using different grade of sand. Okay. Right. So the basic imaging mechanism is the difference in backscatter effectiveness. Okay, so among different kind of atom. Okay, we call that element contrast. Okay, so different atom number will have different backscatter effectiveness. So based on that, we could see the contrast between different areas. And the resolution for the backscatter mode is much lower, 4,000 at most, versus 100,000 for scanning electron mode. Okay. The picture we normally see before is based on backscatter SEM. Okay, this is the concrete sample. This is sand or coarse algae. Okay, and we can see that this is the unhydrated clinker, and we have hydration product here, and we have voids here. Okay, right. So this is a picture of backscatter SEM. Right. So instrument sending electrons, depending on whether it's backscatter or secondary electron. Okay, continuous electron beam focus on a narrow point of the specimen. Okay, and then cause the beam to scanning a raster pattern or a portion of the specimen. Okay, so scanning areas of the specimen using a raster scanning pattern. Okay. And when the beam is focused on a spot, then the rastering speed will begin. Okay, this is over a small square portion of the specimen. So the beam travels from the left to the right, and then pulse. Okay, and then go back to the second line, scanning from left to the right, and then pulse and beginning to the third line. Okay, so typically continue to scan for 512 lines. Okay, right, and based on that, we scanning a certain areas of the sample. Okay, by do the rastering scattering, and that will corresponding to different pistons on the cathode tube, retube. Okay, we have different numbers for different areas. This is from 0 to 10, and then this is from 21 to 30. It should be somewhere between. Right, this is from 41 to 42. Okay. Anyway, any points in the sample will have a corresponding pistons, which is numbered on the tube. And because different atom will have different emission. Okay, and from there we can have a contrast of pistons on the tube. Okay, and here shows how the coefficient of backscatter electrons, okay, which is in the y-axis, is affected by atom number. So different atom has different atom number, and based on the different coefficient, we can see different atoms. Okay, so this is for backscatter coefficient, but for secondary electron coefficient, it is not very sensitive to the coefficient is not very sensitive to the atom number. Okay. And as we mentioned before, we can also use the EDS to see what type of atoms in a certain location. And EDS is short for energy dispersive X-ray spectroscopy. Okay, so the interaction between the electron, either is backscatter or secondary electrons, it will interact with the atoms in the specimen. And the interaction will generate a special X-ray. So we call that characteristic X-ray, okay, which is corresponding to atom number. Okay, so in other words, different atoms will have different characteristic X-ray. Okay, so the X-ray detector will collect this special X-ray, okay, and then sort them by the energy level. Okay, so we could have a display of intensity versus the energy. Right. So if the electron the beam is not moving, is stationary over a spot, so we can have idea of what type of element, what type of atom in that spot. Okay. If the beam is moving, like doing a raster scan, then we can have the average of all the points it is scanned. Right. So for example, we do a stationary scan. This is the point inside for this component, and we know this is etching guide and AFT because the strip patterns of the materials. So this is etching guide formed in the specimen, and from there we can see we have calcium, we could have silica, alumina, and chloride, potassium, and sulfate. Okay, so and this is the atom we can see in that spot of etching guide. Okay, but it cannot tell us the compound. For example, AFT, it cannot tell us we have the compound, but only atom, only atom. Okay. All right, and here tells us how to look at a picture of concrete and cement. So the brightest figure is always unhydrated cement. Okay, so as we discussed before. And the second brightest will be calcium hydroxide. Okay, and the darkest will be porous. The pore will be darkest. And also based on the patterns, for example, etching guide will show the strip case, strip patterns. So we know this is etching guide or AFT. Okay. All right, and here's a large clinker never fully hydrated. As we can see here, this is one cement clinker. The outside is hydrated, but the inside is very bright, which means it is unhydrated. Okay. And we can change the grid scale, grid level scale, to make it or the contrast between different cement minerals the highest. Okay, so if you see a grid scale picture like this, you can use the software to change the grid scale to make the difference between different phases easy to tell. Okay. All right. Okay, so yeah, that's the short introduction of scanning electron microscope. And that's the end of this lecture. Okay, so Derek, any questions?